Welcome to Chapter 12 Test Review. This is to get you guys ready for your Chapter 12 test that will be out this week so that you can do the best that you can do. This is kind of going to be the equivalent to the board notes that I do on the board before our tests and quizzes. So please take notes on this, and then I will have you submit them to me, and then this will prepare you for your test. So if you think back to the beginning of Chapter 12, we talked about three important terms. And if you remember, I used three important items to kind of explain these terms. The first one was called opaque. I used a clay flowering pot, and when we shined a flashlight on it, we saw that none of the light was being seen through it, right? You could not see that there was a light inside of the pot if I had a flashlight shining inside of it. And that's because this type of material absorbed all the light or reflected it so that you could not see through it. So remember, no light goes through an opaque material. Then we talked about a translucent material. And in a translucent material, you can kind of see it. It's a little bit blurry, like I wrote here. So you can't really see clearly what the object is. But if I had something like a lampshade and I had a light bulb inside of it or a candle inside of it, you would kind of be able to make out that there is a light source inside. And that's because translucent material, they transmit light by scattering it. So it's not completely see-through, but you can kind of make out what's inside, and that's because it scatters the light. Lastly, we have transparent material, which means that you are able to transmit the light without scattering it. Therefore, you can see clearly what's inside. So if I have a transparent material like a glass jar, and I put a light bulb inside or a candle or a flashlight, you can clearly see the light coming through. Another example of transparent material is tracing paper, so that when you use tracing paper, you are able to clearly see the item that you are tracing, and then you are able to trace it onto there. We talked about regular reflection and diffuse reflection, if you see over here, in regards to what the surface was that we were looking at and how light was being transmitted off of that surface. So when we talk about regular reflection, we talked about a glass or a mirror, something that has a smooth surface on it. And then because of the smooth surface, when light hits it, it's coming back directly towards the object. Like if you were looking at a shopping window, you could see some sort of a reflection of yourself onto the shopping window because the glass was smooth and it's showing a regular reflection. And then if you're looking at a mirror, you're able to see a complete reflection of yourself because the light from the lamp in your bathroom is hitting you, bouncing off of you onto the mirror, and then the mirror in response is reflecting the light back off of the mirror onto you or into your eye so that you can make out yourself in the mirror. And so remember, regular reflection happens when you have a glass or a mirror, so a smooth surface where the light is pretty much able to be reflected back in the same way that it was reflected in. And then we talked about diffuse reflection, which is basically when you have a textured surface like a brick wall, something that is not smooth. And the reason that it's called diffuse reflection is that when the light is being hit onto this textured surface and then reflected back, it's going in all sorts of direction. It's not coming back as smooth or as in a parallel motion like regular reflection, but it's kind of going all over the place. And so that's why I wrote it goes in various directions. So make sure you understand the difference between diffuse reflection and then regular reflection. Remember that regular, you see a reflection because it is somewhat of a smooth surface and the way that the light is being reflected onto that surface and coming back is more in a parallel fashion, rather than diffuse reflection when the light that is hitting that object and coming back to you is kind of going all over the place. So there is no reflection happening there. Let's talk about mirages. So we talked about in class how if you're driving, or you probably can't drive at this point, you're too young, but if your parent or some other legal person is able to drive, they are, you're in the car, you look out, it's a hot day or a really cold day, and you see something in the distance that kind of looks like a puddle of water. And you can kind of see the reflection of the road or of the car on the road, and you wonder what is that and how does that happen. So that is called a mirage. And basically what's happening is that you have different temperatures of the air layer. So either the air layer on a hot day, the air closer to the road is super hot versus the air on top of it is a little bit cooler. Or on a cool day, like in the winter, you have the road surface as being a lot colder than the air on top of it. And because of the different air layers and the different densities that these airs have, you are able to create a mirage, which is basically you're able to see a reflection of an image in the distance in these various different types of temperatures. And the way that we can actually see this kind of images and so on is because obviously of our eyes. We talked about how our eyes, they have lenses right here, and then in the back of the eyes, this kind of blue part right here is something called the retina. And the retina is able to have two types of cells. They have the cone cells and the rod cells. And I kind of broke it down over here. So you have rods and cones, which make up the retina, and the rods help with nighttime vision, so when this environment is a lot darker, and then the cones help with daytime vision when you have a lot more light to see objects more clearly. The cones are also broken down into 3 different colors: blue, green, and red. You don't need to know the specifics of this for the test, but this is just kind of to jog your memory. But just remember, rods and cones make up the retina, which help you to see whether it's nighttime or daytime. Let's talk about Roy G. Biv. So when we talked about Roy G. Biv, we talked about it in reference to visible light. So this is pretty much how visible light is broken down to. We can clearly see this when we use a prism. When white light goes into a prism, it gets broken down into these colors. And then we also talked about how red light has the longest wavelength, so it's the least refracted. That means it's the least bent. And then we talked about violet being the shortest wavelength of light, and so it's refracted the most. So this is important just to know which one is the shortest and longest wavelength, and then that these are the colors of visible light that we normally can't just see without a extra kind of instrument like a prism, or when you see a rainbow because of the water droplets, and so on and so forth. So let's move on to the filter. So what exactly is a filter? A filter is a transparent material that selectively transmits light. So when I have, for example, like I wrote over here, if I had a blue filter and I'm shining a white light through that blue filter, okay, that blue filter is going to cause that white light to be transmitted through that blue filter and cause that white light to become blue. So let me repeat that again. If I have a blue filter and I have a white light shining through that blue filter, it's going to transmit that blue light and those blue wavelengths through so that that white light is no longer white, but it's going to be blue. And if you look at an object like an apple, we also talked about how when you look at an apple that's red, the reason that the apple is red is not because it's absorbing the red light or red wavelengths, it's because the apple is reflecting the red wavelengths, right? So the apple is red because of the red wavelength that it is reflecting. So right here I said red apple is red because of the red wavelength it reflects, and the color of the object is determined by the light it reflects. So this red apple is reflecting the color red and not absorbing it. Incandescent light. Incandescent light, we talked about in class, was pretty much a light bulb that has a filament inside, and that filament is called tungsten. So what happens is the light, when you turn on the light bulb, the filament, the tungsten gets heated up, and when it gets heated up, it shows visible light so that we can see inside of a dark room. So that's pretty simple, nothing really complicated about incandescent light. But when you have a fluorescent light, it gets a little bit interesting and a little bit more complicated. Fluorescent light, we talked about, is actually way more efficient and uses a lot less energy than a incandescent light. So we talked about how people who run businesses, who have schools and hospitals and offices that are on long-term and operating for long hours use fluorescent light more than incandescent light because of the more efficient it is and the less energy that we use. So if you remember, we looked up in our classroom and we saw that our classroom was lit up by fluorescent lights. So how does these fluorescent lights actually work. So I did my best job to draw a fluorescent light bulb. So I'm just going to explain the structure. So when you have a fluorescent light bulb, on either end you're going to have electrodes. And these are what are going to connect to the circuit. So these are going to be connected and the circuit's going to run through this bulb. Inside of this fluorescent light, you're going to have something called phosphor, like phosphorus, right? And they kind of paint it on the inside of the light, and we're going to talk about why that is super important. And then as the current is running through this, when the electrodes are connected to the circuit, you're going to have a release of electrons. So let's talk about what happens when you are plugged into a circuit. So the first thing that's going to happen is that it's a little tilted. You're going to have electrons that are going to give off. Electrons are going to be emitted when the electrodes are connected to a circuit. So when these electrodes right here are connected to a circuit, you're going to have electrons, I can draw them right here, that are going to be floating around because of the current that's flowing through it. Then you're going to have those electrons collide with a gas that's inside of the bulb. So fluorescent lights contain a gas at a very low pressure. And so when these electrons are emitted because of the electrodes being attached to the circuit, these electrons are going to hit those gas atoms that are already inside of the fluorescent light bulb, and that's going to cause something called UV rays to be emitted. UV rays is just an abbreviation for ultraviolet radiation, okay? So I'm going to say it again. These electrodes right here are going to connect to a circuit. When they are connected to a circuit, electrons are going to be released inside of the light bulb. The light bulb already contains a gas, so when the electrons are emitted, those electrons are going to collide with the gas atoms and release UV rays or ultraviolet radiation. So now, where does the phosphorus come to play that's painted inside of this bulb? So what's going to happen is when that UV radiation is released, the phosphorus inside of that bulb is going to absorb that UV radiation, and it's going to give off visible light, which is what we see when we're in the classroom, okay? So I'm going to repeat it one more time. Electrodes are connected to the circuit. They release electrons. Those electrons collide with the gas atoms that are already inside of the light bulb. And those gas atoms are at a lower pressure than normal. And that's going to cause UV radiation or UV rays to be emitted. Phosphor that's painted inside of the light bulb is going to absorb that UV radiation, and it's going to give off visible light that we can use to see in our classroom or in another kind of office. Now, some bulbs may have different types of gas. So for example, we talked about how some bulbs may have something called neon gas, and that can give off a different color. And what happens is you have those neon gas particles floating inside of the bulb. Electrons, when they are turned on, when the bulb is turned on, these electrons that are emitted will hit these neon gases, and then they will produce light. Incoherent light versus coherent light. So incoherent light and coherent light, you can kind of tell in their name itself. Incoherent light is kind of when the light waves contain more than one wavelength and they are not lined up. So you can see how the crests, which are the tops of the waves, and the trophs, which are the lower part of the waves, they're kind of all jumbled together. There's no pattern, there's no unison in their syncing abilities. They are kind of just crazy and all over the place. So that's incoherent light, okay? Coherent light, on the other hand, is a lot more organized, and these light contain wavelengths that are aligned, which means the crest, which is the top of the waves, are all lined up, and then the trophs are all lined up, so they're very well organized. So an example of coherent light is actually lasers. Lasers are produced when you have atoms that are identical to each other, and when they become stimulated, they emit coherent light. So they emit light that have waves that are very identical to each other. An example of what uses lasers is CDs. CDs use lasers to convert information to electrical signals, and then they are also able to store a lot of information in something called these tiny pits. So that's an example of how lasers are used in our day-to-day activities, even though CDs are not really used that much anymore. But back in the day, they were. So let's move on to primary colors of light. So primary colors of light are red, green, and blue. And when you combine these primary colors of light, they make white light. They have to be in equal amounts, so you can't have more red than green, or more green than blue, or more blue than green and red. In equal amounts of red, green, and blue, you can make white light. On the other hand, primary pigment colors are magenta, cyan, and yellow. But when you mix these primary pigment colors together, you're not getting white light, you're getting a black dark color. Okay, so that's the difference between primary pigment colors and then primary colors of light. So when you have a question, make sure you're focusing if is it primary colors of light, primary colors of pigment, and then make sure you also know the difference: magenta, cyan, and yellow. Cyan's more of a bluish color, it kind of looks green on here. And then here you can just see it's red, green, and blue for light. And then an example of using these primary pigment colors is like paint. You can have blue and yellow paint to make green. That's just an example of how you can mix different types of these colors to make different color combinations. I remember telling you guys in class that when you have a printer, these are the 3 colors that they use, and with these 3 colors they can make almost every color of the rainbow or every other color combination you can think of. So that's why you don't need every single color when you are buying ink for your printer. Polarized filters are kind of the last thing that we ended up off on talking about, and polarized filters are a huge blessing because you can use them to block glares from when you are driving or when you're looking at the lake that I used as an example from the previous video. And when you have 2 polarized filters and they're overlapped at right angles, so you have one that's going horizontal, so if you're driving and the glare from the road is going horizontal, and then say you have glasses on that are vertical, they're actually making right angles, and that's going to cause all of the light to be blocked, which is not a good thing if you are driving, okay? So you don't want to have polarized filters going at right angles because then you're blocking all the light. But on the other hand, if you have, if you're driving and the glare from the road is going up at a horizontal, horizontally, and your glasses are also painted horizontally, then you're going to be able to block off some of the light so you can still see, but you're not going to be blinded by the glare. So a lot of people were confused on this, so I just wanted to make sure you guys understand that because there is a question on this on the test. Make sure you also know that polarized lights vibrate in one direction. So let's move on to angle of incidence, angle of reflection, and then optical fibers and total internal reflection. So let's focus on angle of incidence and angle of reflection. This was one of the first things that we talked about in the chapter, but I thought it would go well with the total internal reflection and optical fibers to kind of make more sense. So if I have a mirror right here, this is my mirror, and I'm shining a light at the level of normal, at the line of normal. The light that's going to go in and hit the mirror is going to hit at an angle of incidence, okay? So that's what's hitting a surface. So the surface in this case is a mirror. But the light that's going to be reflected off of the mirror is going to be called the angle of reflection. So that's the light that's leaving the surface. So angle of incidence is the light that hits the surface. Angle of reflection is the light that leaves the surface. Now, the cool thing about this is when you're hitting something like a mirror, the angle of incidence and the angle of reflection are going to be the same, okay? So if I have 20 degrees up here, it's going to be 20 degrees down here. If I have 50 degrees up here, it's going to be 50 degrees down here, all right? So they're going to equal the same. Now, we talked about what happens if I have a light source underwater. If I have this flashlight and it's beaming out this light underwater, and I'm hitting the surface of this water, so the boundary, right, between the air and the water, I'm going to have something called a total internal reflection. A lot of you guys totally understood what this was based on your homework answers and stuff like that. And basically total internal reflection is going to be greater than your critical angle, which is a lot smaller. And in total internal reflection, you're reflecting all of the light that is hitting this boundary between the water and the air back into the water, as if almost there was a mirror here and it's being completely reflected back in. Okay, so that is what total internal reflection is. I just wrote down a brief example of that, or in words, what I just said. So total internal reflection is light traveling from one medium to another, but light is completely reflected at the boundary between the two materials and back into the water. So in this case, the two materials would be the air and the water. So when light is hitting right between there, it's being reflected back into the water, almost like there is a mirror. And then refracted, when I talk about refracted, that I'm just saying that the light waves are changing speed from one medium to another. So that's a definition of refracted. Remember when I said how light is being bent? That's also another definition of refraction. But what refracted means in this term and in what we're talking about is how light waves are changing speed from one medium to another. So when they are changing speed from air into the water, you can see refraction, which is the bending of the light, because it's traveling faster in air and slowing down in water. So that's why you have that bend that we also saw in some of the experiments where I had the wooden stick inside of the beaker. You could see how the stick looked kind of distorted because of the refraction that was happening. And then to end off everything, we have optical fibers, which is basically a way to convey waves from one spot to another that may be longer or more complicated to get to. And optical fibers also use total internal reflection to commit these waves from one area to another. And that's a really great use in our lives today, whether it's through internet or on the phone, so on and so forth. So that's it for your chapter 12 review. Make sure you copy all these notes, and then good luck on your test.